Welcome back. Today we have our eighth video of our series of design key value store. Today we talk about the failure detection in our system. Before I start, if you didn't watch the previous video, I highly recommend them. I recommend you to watch them. However, if you watch them and you just don't remember what we was talking about, I will just make a quick recap of what we have said in the last 7 videos. So before starting, I'll just make a quick recap. Our series starting with solving a problem, a system design problem that was design a key value store, and we said that all the time in system design interview, all the time you'll find the questions are pretty vague. So our job as an interviewee is to ask clarifications questions and follow some framework and follow some steps to make sure that we are designing the things that our interviewer wants us to design. So we have this framework that we're using. We first understand the problem, after that propose a high level design, and after that get deep dive on specific components that our interviewer wants us to get a deep dive on them, and after that we have a wrap up. So if we talk about the understanding the problem, because it's the most important one, we want to ask from 5 to 7 questions. I will not go through them right now because there is a video talking about them, but long story short, from this questions we have our functional requirements and our non-functional requirements, and you want to make sure that after you put non-functional requirements and the functional requirements, and even though if you think it's the best functional and non-functional requirements, you have to ask your interviewer, which is whether that is there anything that we are missing or not, to make sure that we're designing the exact thing our interviewer wants us to design. So we don't want to make any assumption at all when it comes to in system design interview. And after that we talked about the cap theorem. When we talked about the proposal high level design, we talked about the cap theorem, and we said that it's possible for any system to guarantee that to have three possible the three things together. It only can two, and the other one will be sacrificed. So maybe you have AB system, which is availability and partition tolerance for sacrificing the consistency, and we have a CP system, a consistency and partition tolerance for sacrificing the availability, and we have availability AC system, availability and consistency and sacrificing the partition tolerance. And with the AC system is not a real world application because a partition tolerance is not something that we can avoid. So it's all the time we choose by AB and CP, and because our functional requirements was that our system will be highly available, so we choose AB and acceptable consistency, or like let's say tunable consistency. So because that would change an AB, and for the functional non-functional requirements, we take a hint of what our application will look like. Of course, there is no one design fits all, but we just are trying to make the right frameworks so you can use this framework with as many system design interviews as you can. And after that, we talked about the deep dive. We talked about the data partition, that instead of sorting all of our data in one server, we sort our data we partition our data and store them in a hash ring, using consistent hashing, and store the key with just we put the key in the hash ring and you go clockwise and store the key there basically. And to make sure that we have a maximum availability, we will do data replication, so we store our key in multiple nodes. And after that we talked about the consistency problem and how we can solve this consistency problem. We have the quorum consensus that solve this consistency, that we have the coordinator. It just give each server a vote power, and requires a quorum size for the quorum size for the right, let's say 3. So the coordinator is waiting at least for 3 successful requests to make sure this request is fulfilled or is successful or not. And after that we talked about the consistency model, and we talked about the strong and the weak and eventual consistency, and we talked about how we will use the eventual consistency and the problem come with eventual consistency with is the some inconsistent data, maybe like when the clients two clients update the same data at the same time, and how we can solve it. And we talk about the vector clockwise and how versioning is helping us to solve this problem. And today we will talk about handling failures. Okay, so handling failures right now, we wanna, like, with a large scalable system right now that we have, failure are not only uh, just something random happening, or some happens like every once in a while. It's like it's commonly to have failures. So uh, we should have some techniques to handle failures. One of the techniques that we have, that it's in the distributed systems, it's it's not possible to know if a server is down because one server set is down. So instead of doing that, we do something like you see right here. It's that usually we it requires maybe like one or two or three servers to independent servers or independent resources to mark a specific servers down. So basically we have S0, and S0 is connecting with S1, S3, and S1 and S2, connecting with S1, S2, and S3. You see with the white, with the yellow, and you find S1 is connecting with S3 and S0 and S2, and you finding S3 is connecting with S0 and S1 and S2 with the red row. And the problem that comes with this will work, but the problem when have a scalable big application, and if our hash ring is pretty big, this is not a good solution, basically, because it's not built with scale. If with scale, it will be pretty complex. So the solution that we can use, wait a minute, is something called a gossip protocol. So first of all, what is a gossip protocol? The gossip protocol is decentralized and probabilistic protocol used for failure detection and information dissemination in distributed system. It's designed to quickly and effectively detect failures and propagate information across network of nodes without relying on any centralized authority. So we have maybe let's just take about overview of how it works. First of all, that we have um, if we look at this one here, so uh, let's just scroll, yep, like that. Okay, using a better, like, let's say that each node, it's maintain a node membership in the list. Okay, just because we have to see both of them because it's quite important. Let just, okay, I guess, I hope this you can see both of them right now. Okay, so each node that you're seeing right now maintains a node membership in the list, which contains a membership ID and the hard count and the time. Okay, each node periodically increments its hard counter. Okay, this increments its hard counter beat. Each node periodically send heartbeats to a set of random nodes. Okay, which in turn propagate to another set of nodes. So we send, like, for example, S0 will send a random request to S1 and S2, S3, sorry, and S3 will send to S5 and S4. And once a node receives a heartbeat membership list, it's updated to the latest info. So let's say that we're updating it right now. So basically, if S0 is send S1 a random heartbeat, it will update it if it's successful. And also for S3, if send to S5, it will update it if successful, and S4 it will update it if it was successful. So for this one, if the heartbeat has not increased, for let's say for S2, they sent S2 and S2 was offline, so S2 didn't increase their heartbeats. So if the heartbeat has not increased for more than a specific amount of time, this member or this resource is considered as offline. So if you see again here, we have S nodes is 0, is maintains a membership list shown as in the left side. Okay, see right now. And S0, notice the S2 membership ID, this one, okay. Herd count has not increased for a long time. It just has, if you can see, it didn't increase for a very long time. So node S0 sends a heartbeat that includes S2 info to a set of random nodes. Once other nodes confirm that S2 heartbeat counter has not been updated for a long time, node S2 is marked down, and this information is propagated to another node. So this is how we can handle or how can detect failures. And that's it for this video, and I guess the next video will talk about how to handle the temporary failures and how we can solve this issue. And that's it for this video, and I hope my solution was quite good. If you like the video, make sure to subscribe, hit the notification bell, and give me a like and thumbs up so you never miss a video, and see you in future videos.